All right. So this is the second part of lecture for chapter 13. Okay. So here you are going to learn about gas laws and the kinetic theory of gas. Okay. All right. So in the last lecture, you learn about how object changes with the temperature, right? You remember that object expands when the temperature increases and contracts when the temperature decreases. Okay. And this equation you already see in the last lecture, and this equation we used to explain the volume expansion or the volume contraction. Okay. Now, when we deal with gas, this equation is not very useful. Okay, it is not useful for two reasons. The first one is this one. Okay, the volume of gas depends on the volume of the container. Okay, the same for same amount of gas, you can use different container. I mean, you can same amount of gas can fit in different size containers. Okay, so that's why I mean the delta V or the original volume V0 could be different for a different size container for the same amount of gas. Okay, and also the expansion can be so great. Okay, all right. Now what to do when we deal with gas? Okay, when we deal with gas, we need to determine a relationship between volume, pressure, and temperature. Okay, and such relation we called equation of state. Okay, so equation of state is basically combination of three gas laws. Okay, that you are going to learn now. So three gas laws are Boyle's law, Charles' law, and Gay-Lussac's law. Okay, so let's learn one by one. Okay, so what is the Boyle's law? Boyle's law tells us that when temperature T is constant, then the volume V of a fixed quantity of a gas is inversely proportional to the absolute pressure P. Okay, so here you see V is inversely proportional to P. So here V is the volume and P is the absolute pressure. Okay, so what is the absolute pressure? Absolute pressure is basically the atmospheric pressure plus the gauge pressure. Okay, so if you forget, please review chapter 10 for absolute pressure. Okay, the next one is the Charles law. So what is Charles law? Charles law is very similar to Boyle's law, but it is the relationship between the V and T. Okay, so in Boyle's law, the temperature was constant, but here the pressure is constant. Okay, so when the pressure is constant, then the volume of a fixed quantity gas V is proportional to the absolute temperature. So here T is the absolute temperature. Okay, so what is absolute temperature? So in the last lecture you learned about absolute temperature, and absolute temperature is the temperature measured in Kelvin scale. Okay, so measured in Kelvin. Okay, that is the absolute temperature. And the last one is the Gay-Lussac's law, and it is the relationship between the absolute pressure and absolute temperature. Okay, so pressure and temperature are proportional to each other when the volume is constant. Okay, now when you combine these three equations, you get this equation: PV is proportional to T for a fixed amount of gas. Okay, now before I write an equation using this, let me talk about amount of gas. Okay, and then I am coming back to write an equation which relates the absolute pressure, volume, and temperature. I mean absolute temperature. Okay, now here I'm going to talk about the amount of substance. Okay, amount of substance is measured in mole. Okay, mole is the standard international unit for amount of substance. Okay, do not confuse this with mass. Okay, mass and amount of such substance are related. I will show you in this slide, but they are two different things in physics or in chemistry. Okay, so mole is the SI unit for amount of substance, and we use just MOL to represent mole. Okay, now what is the definition of mole? There are two definitions of mole. Okay, so the first one tells us that 1 mole is the amount of substance that contains this amount of object. Okay, 6.022 times 10 to the power 23 object. Here object means the atoms or the molecules. So what it means in 1 mole of some molecules, or 1 mole of some atoms, means there are 6.022 times 10 to the power 23 molecules or atoms. Okay, and it has some special name. This number has some special name. This number is called the Avogadro's number, and we use n subscript a to represent Avogadro's number. Okay, so Avogadro's number is 6.022 times 10 to the power 23. Okay, all right. Now another definition for mole we use is this one. Okay, and this is the relationship between mole and mass. Okay, and this definition tells us that the mass of 1 mole of carbon 12 atom is equal to 12 gram. So here you see that mole, and you see how mole and mass are connected. Okay, so again here we are using carbon 12 atom as a reference. Okay, and mass of carbon 12 atom is equal to 12 gram. Okay, um, so now with this definition you can also show that mass of 1 mole of any atom, okay, any atom, is equal to, so if you want to know what is the mass of 1 mole of any atom, you need to know what is the atomic number of this atom. Okay, let's say we are talking about oxygen atom. Okay, and the atomic number of oxygen is 16. Okay, so you need to know what is the atomic number. So once you know the atomic number, the mass of 1 mole of that atom will be just atomic number gram. Okay, so if the atomic number is 16, then the mass will be 16 gram. Okay, so for example here, this is molecule: hydrogen molecule, oxygen molecule, and carbon dioxide molecule. Okay, so hydrogen molecule contains 2 hydrogen atom. Okay, 2 hydrogen atom, and hydrogen's atomic number is 1. So that means 1 mole of hydrogen atom, mass of 1 mole of hydrogen atom is 1 gram. Okay, now in hydrogen molecule we have 2 hydrogen atom, so 2 times 1 gram is 2 gram. Okay, similarly for oxygen it is 16 grams. So here you see that a mass of 1 mole of oxygen atom is 16 gram. Now for oxygen molecule, because it has two atom, okay, so it will be 2 times 16, that is equal to 32 gram. Okay, similarly 1 mole of carbon dioxide is 1 carbon is 12, the atomic number of carbon is 12, and then for 1 oxygen it is 16. So we have 2 oxygen, so 2 times 16 is 32, 32 plus 12 is 44 gram. Okay, similarly you can show that the the mass of 1 mole of hydrogen, I mean water molecule H2O, okay, is 2 gram for 2 hydrogen atom, and 16 gram for 1 oxygen atom. So altogether it is 18 gram. okay, and so on. So with this, you can determine the mass of uh, 1 mole of any atom or any molecule, okay, if you know the atomic number. All right, the next thing we need to know is if we given let's say if we are given and the mass of certain amount of a sample, okay. So if we are given the mass of certain amount of sample, then how to know how many mole are there? How many mole are there? Okay. So this is the equation how you can determine it. For example, if you are given 90 gram of water, okay, and you want to know how many mole are there in 90 gram of water. So what you have to do, you have to divide this by this mass of 1 mole of hydrogen, I mean 1 mole of water molecule, and you know that is equal to 18 gram. Okay, so 90 divided by 18 is 5. So in 90 gram of H2O or in water, there are 5 mole of water molecule. Okay, similarly you can show that for 132 gram of carbon dioxide there are 3 mole. Okay, so 132 divided by 44 is equal to 3 mole. Okay, so using this you can determine for any sample if you know that know the molecular mass. Okay, all right. Now the amount of substance that you learn in the last slide is determined by, I mean, represent by this symbol, small n. Okay, small n is the amount of substance or mole, number of mole. Okay, now the equation PV is proportional to T. This equation was valid for fixed amount of gas, but in general, if you want to add the amount of substance, the equation now becomes PV is proportional to N times the absolute temperature. Okay, it's a little bit different. Here we added N, the number of moles. Okay, so now we are ready to write an equation. So now if I want to get rid of the proportional sign and write an equation using an equal sign, we need a proportionality constant, right? So here the proportionality constant is R, okay? And R is called universal gas constant, okay? And it is the same number for any ideal gas. Okay, and the value of the universal gas constant is this one, R equal to 8.314 joule per mole per Kelvin. Okay, and this PV equal to nRT is called the ideal gas law or the equation of state for an ideal gas. Okay, so when we later when I mention about ideal gas law or the equation of state, by that I mean basically PV equal to nRT. Okay, now this gas, although it is for ideal gas, we can use this for real gas. Okay, with some restriction. Okay, I mean, you cannot use always this equation for the real gas, but if the temperature is not close to the boiling point, or if the pressure is not too high, then experimentally we see that this is, I mean, this equation can be used for any real gas. Okay, the restriction is we cannot use this when pressure is too high or the temperature is not close to the boiling point. Okay, all right. Now there are two other forms we can write this equation. Okay, now the first one is when n is also constant. I mean when when the amount of substance is fixed. So when the amount of substance is fixed, then n is constant, r is already a constant, right? Then PV equal to nRT. In this equation, this term is constant. N times R is constant because it's for a fixed amount of gas, right? Then we can write this equation as this: PV over T equal to nR, okay? And nR is a constant, okay? Now, sometime instead of writing this is useful. P1 V1 T1 is equal to P2 V2 T2, okay? Because P1 V1, the combination of P1 V1 over T1 is constant, okay? So let's say we measure pressure, volume, and temperature for a fixed amount of gas at some time, okay? And let's say they are P1 V1 and T1, and later at some point we also measure, and that time let's say the pressure, volume, and temperature are P2 V2 and T2, okay? Although pressure, volume, and temperature may be individually different, but the combination PV over T will be constant, okay? That you see that that is true if n is fixed, okay? If n is constant, okay? If n is constant, then we can write something like this, okay? And this is another way to write the ideal gas law or the equation of state, okay? All right. So in some numerical problem, you probably see STP, okay? And STP means the standard temperature and pressure, okay? So in chemistry and in physics, by STP we mean the temperature, the freezing temperature, okay, in Kelvin scale, okay? So freezing temperature is 0°C, right, or melting point. But uh, you know that degree Celsius is not the standard international unit. So the standard temperature is the freezing point, but in Kelvin scale, and that is equal to 273 Kelvin. And standard pressure means the 1 atmospheric pressure, and 1 atmospheric pressure in standard international unit is 1.013 times 10 to the power 5 Newton per meter square, or sometimes this unit is also called Pascal, okay? So Pascal is PA. So 1 PA is equal to 1 Newton per meter square. So if you see Pascal in some problem, in some numerical problem, you just need to know that 1 Pascal is equal to 1 Newton per meter square, okay? All right. So there is another form of the ideal gas law, that is PV equal to NKT. So this is the another form. Now here N is the capital N and R is replaced by K, okay? So in nRT, N was small n, okay? And small n means the number of mole, but here capital N means the number of molecule, okay? So to understand this, let's assume that there are n mole of gas, okay? So there are n mole of gas, okay? And we know that in 1 mole there are this number of molecules, right? The Avogadro's number of molecules. So in 1 mole, if there are a number of molecules, then in n mole there will be n times n a number of molecules, okay? And that is equal to n, okay? As you, I mean, at the beginning I told you that this n means the number of molecules, okay? So that means na equal to n, and here if you solve it for n, it gives you something like this: n, the number of molecules, over Avogadro's number, Okay, now if you substitute this N to the ideal gas law, you get this, right? And then R, if you simplify it little bit, you get something like this. Okay, and here you see that R is a constant and Na is another constant. Okay, so R is a universal gas constant and Na is the Avogadro's number, which is another constant. So constant divided by another constant is another constant. Okay, so this ratio has some special name. We call it K, small k, and small k is equal to 1.38 times 10 to the power minus 23 joule per Kelvin, and it is the Boltzmann constant. Okay. So now if you replace this ratio by K, you see that PV equal to N capital N times the Boltzmann constant times the absolute temperature. Okay, so sometime this equation is also used to represent the ideal gas law. Okay, so if you know the uh, total number of molecules, then you will be using this equation. If you know the number of moles, then you will be using PV equal to nRT. Okay, so depending on which you know, you can use either PV equal to nRT or PV equal to nKT. All right, now the kinetic theory. So kinetic theory is a big derivation, and here in the lecture note, in the study guide, I already derived everything, but I'm not going to teach you here. I'm just going to talk the final form. Okay, so please go through it if you want. Okay, if you don't want, it's also okay. But if you want to learn how I derived the kinetic theory, please go through it. Okay. So the final form for the kinetic theory is this one. Okay, so this one is the final form, and it tells us the kinetic energy. Ke is the kinetic energy, and the bar on top of the kinetic energy means it is the average kinetic energy. Okay, and remember that kinetic energy is this half mv square. Okay, so in physics 1, you learn about that the kinetic energy is equal to half m times v square, where m is the mass and v is the speed. Okay. And the kinetic theory of gas tells us that the average translational kinetic energy of molecules in a random motion of an ideal gas is directly proportional to the absolute temperature of the gas. Okay, so here T is the absolute temperature. Okay. Now, let me show this simulation. Here, I'm just going to show how this equation makes sense. Okay, I mean, of course, you can go through all the steps and come to this point, kinetic energy equal to 3/2 kT. As I'm not deriving it, let me show it in this simulation how kinetic energy or the average kinetic energy is related to the temperature. Okay. Okay. So here you see in the left hand side we have a thermometer, and basically the right hand side or the middle picture is basically shows uh, in a big scale. Okay, so you know that in a thermometer, normally in a glass thermometer or tube thermometer, this red part is basically mercury. Okay, now what happened when the temperature increases? Okay, so you see, I mean, at this point the temperature is low. Okay, uh, and this means a high temperature. Okay, temperature low and temperature high. Now what happened here when the temperature is low? Okay, so here you see that the red molecules, okay, the mercury molecules are not moving too fast. Okay, they are moving, but the motion is not too fast. Okay, as the temperature is increasing, you see the motion, the molecular speed is also increasing. Okay, so you see that higher the temperature, higher the speed of the molecules. Okay, so higher the temperature, higher the molecular speed. Okay, and you know that the molecular speed is somehow connected to the kinetic energy, right? Kinetic energy is equal to half mv square. That means higher the speed, higher the kinetic energy, right? And here you see that at this point the speed is too much. Okay, speed is high. High speed means high kinetic energy, and you see it in turns tells us that the temperature is high at this point. Okay, when the temperature is so at this point you see that the motion is not I mean the speed is not that great here. Okay, speed is lower than before now. Okay, that means the kinetic energy is now lower, and that tells us that the temperature is also lower. Okay, because they are proportional to each other, that we see from the kinetic theory of gas. Okay, so although I didn't derive it, but this simulation nicely demonstrate that the kinetic energy or the average kinetic energy is proportional to the absolute temperature. Okay, all right, now I want to derive the speed. Okay, derive an equation for speed. Okay, and to do that we need to know that kinetic energy is I mean average kinetic energy is equal to half m v square average. Okay, so here we use the average v square. Okay, because the kinetic energy is average. So average kinetic energy equal to half m average v square. Okay, and that is equal to 3 over 2 kt. All right, now you see that you can cancel 2 and 2. So you have here m v square equal to 3 kt. So v square is equal to 3 kt over m. Okay, and square root of v square is equal to square root of 3 kt m. Okay, and this has a special name because it is the square root of the square of the average velocity. Is called the RMS speed. Okay, RMS speed means root mean square. Okay, root mean square. So it is the root mean square speed. So the root mean square speed is equal to square root of 3 kt over m. Okay, all right. The next thing I'm going to talk about the distribution of molecular speed. Okay, so using the kinetic theory of gas, James Clerk Maxwell derived the speed of molecules, derived the speed of molecules in a gas, and he showed that the distribution is something like this. Okay, in the x-axis we have the speed, and in the y-axis we have the number of molecules. Okay, and here this graph tells us that this peak point is the most probable the speed. Okay, in a when we have a large number of molecule, most of the molecules molecular speed for I mean uh, um, is around the most probable speed, but this most probable speed is different than the RMS speed. RMS speed is little bit higher than the most probable speed. Okay, and he also shows that for higher temperature, this graph shifts to the right. So you see this graph is at lower temperature and this graph is at higher temperature. You see that the peak shifts, okay, to the right. So here for this one, this is the most probable speed, and for this one, this is the most probable speed. Okay, and RMS speed will be, of course, different, and it will be somewhere here for this one and here for this one. Okay, I have a simulation. You can also see it from the simulation. Let's see what it is. So we have two distribution. The red one is at lower temperature. So the higher the number here, higher the temperature. Okay, so let me, so 20 means much higher temperature, and let's say 9. Okay, so you see that when you increase the temperature scale, the motion, the speed increases. Okay, the molecules are moving quickly than earlier. Okay, and if you plot the distribution, it will be something like this, and you see that it is the Maxwell's distribution of speed. Okay, and you see that the red one is at lower temperature, so the peak is to the left, and for the blue one, the peak is little bit shifted to the right. Okay, so as in the slide, I already mentioned that at high temperature, the graph shifts to the right, and this simulation also shows it nicely. Okay. Okay. Now two more thing. One is the PV diagram, and another is the PT diagram. Okay. So PV diagram is basically is the another way to representing the Boyle's law. So you remember that Boyle's law tells us that when the temperature is constant, then P is inversely, V is inversely proportional to P. Okay. Now, if you plot these for a fixed amount of gas, it will be something like this. And of course, the temperature T is constant. So this diagram, in this PP diagram, T is constant. Okay, so this is basically the Boyle's law. And if you remember, Boyle's law is for an ideal gas. And at some point, I mentioned that the gas laws, um, uh, PV equal to nRT or PV equal to nKT, basically for ideal gas, and for some I mean, with some restriction, we can use this equation for real gas. Okay, now let me talk about that. Okay, now here the right hand side graph is the PV diagram for a real gas and 4 different temperature. Okay, so A, B, C, D means it is graph A is for at temperature TA, B is at temperature TB, and so on. And the order is this: TA is higher than TB, and TB is higher than TC, and TC is higher than TD. Okay, and boiling point is somewhere here. Okay, so remember that at some point I mentioned that when the temperature is not close to the boiling point and pressure is not too high, then we can use the ideal gas equation for real gas. And here you see that A is far from the boiling point, and you see that it is almost nicely um, follow the ideal gas equation. So ideal gas equation is basically this dotted line, and here for low pressure, it's basically exactly follow the same curve. Okay, so ideal gas equation is this one, but when the pressure is little bit high, then it deviates. Okay, so it makes sense. Okay, now number B is little low temperature, which is close to the boiling point. Okay, and it is more deviate than A. So here you see this dotted line is the ideal gas equation, and the straight line, solid line, is for real gas. Okay, C and D is even more distorted. Okay, now let's talk about C. C has some special property. Okay, so temperature of this temperature of this line is Tc. Okay, Tc is called the critical temperature. Okay, now when the temperature is above the critical temperature, I mean this one and this one, okay, then you see that it it behaves more close to the ideal gas. Real gas behave more close to the ideal gas, but below it, it's not that much. Okay, and there is another thing we need to understand here is this one. So gas has two names. Gaseous state has two names. One is vapor and another is gas. Okay, and it's basically um, um, how far the temperature of the state from the critical temperature. If the temperature is below critical temperature, okay, then you can change the gas to liquid by just changing the pressure. Okay, so gas will change to the liquid phase if sufficient pressure is applied. Okay, and this time the gaseous state is known as vapor. If the temperature is higher than the critical temperature, no amount of pressure can cause a gas to change the phase and become liquid. And this time the gaseous state is known as gas. Okay, so you see that depending on the critical temperature, the gaseous state has two names. One is gas and another is vapor. So when it is in vapor, okay, you can apply sufficient pressure and you can change the phase um, from um, from gas to liquid, or vice versa. Okay, but if it is above the critical temperature, you cannot do that. Okay, that time we call it gas. So the next slide, I have a table, and this table shows us the critical temperature and critical pressure for some substances. Okay, you may, in some numerical problem, you may see water and carbon dioxide. We may not do problem with the other materials. Okay, the last thing is the PT diagram. Similar to PV diagram, there is also PT diagram, and PT diagram is also known as the phase diagram. Okay, and it shows all the three phases. As you know that there are three phases: solid, liquid, and gas. Okay, so here this graph shows us the PT diagram or the phase diagram of water. Okay, and here you see that this line separates the solid and liquid phase. This line separates the liquid and gaseous phase, and this line separates solid and gaseous state. Okay, now these lines basically tell some important properties of water. Okay, for example, let's first consider this line. Okay, and this line tells us the melting point. Okay, so all this number on this line are the melting point at a different pressure. Okay, so for example, at 1 atmospheric pressure, the melting point of water is 0 degrees Celsius. Okay, and we know that. But if the temperature, if the pressure is different, then melting point will be different. For example, at 200, no, not 218. So it looks like at 0.006 atmospheric pressure, the boiling, I mean, the melting point is this 0.01 degrees Celsius. Okay, so you see that 0 degree Celsius is the melting point of water when the pressure is 1 atmosphere. Okay, if the pressure is different, the melting point will be different. Okay, something for this line. This line tells us about the boiling point. For example, at 1 atmospheric pressure, the boiling point is 100 degrees Celsius. Now if you change the if you change the pressure, the boiling point will be different. Okay, for example, for this pressure, the boiling point will be this one. Okay, and so on. And the last one is this line. This line is separating solid and gas. Okay, so we can also go directly from the solid to gas, or gas to solid. Okay, and the process by which we can go from solid directly from solid to the gas, it's called the sublimation. Okay, so this line is basically the sublimation temperature and pressure. Okay, and this point, okay, at this point all the three lines meet. Okay, and that means at this point all the three phases, all the three states, I mean the solid, liquid and gas, can stay together. Okay, and it is called the triple point. Okay, for water the triple point is the temperature is 273 Kelvin and pressure is 6.03 times 10 to the power minus 3 atmospheric pressure. Okay, so that's it for this chapter. um, in the next lecture I will be solving some of the classwork problem. Okay, and then we are going to start a new chapter. Okay, all right, so I'm going to stop here.